Alright, so here's how we figure out what type of forces are going to hold molecules together, different molecules of the same stuff together. And what we first have to do is figure out if this compound is polar or non-polar. And if it's polar, what type of bonding is going on here. So for CH4, the Lewis structure, if we did the math, we would find that we would have 8 shared electrons or 4 bonds. So we have to look at to see whether these carbon to hydrogen bonds are polar. And for that we need to know our electronegativity. So we look up the difference between carbons and hydrogen's electronegativity. We find that it's 0.4. And 0.4 or lower for a difference of electronegativities is going to give us a non-polar bond. So all these bonds are non-polar. So that means if we look to the flowchart to figure out if a molecule is polar, well, are there polar bonds? Nope. So that means the molecule is non-polar. You'll get that for the quiz tomorrow. So the molecule here is non-polar, so to figure out what type of intermolecular forces are present, we looked at this little flowchart, types of intermolecular forces. Is there a polar molecule? Nope. So that means that we're going to have dispersion or London forces, the weakest of them. So London or dispersion forces, and that's because the molecule is nonpolar. If we look at CH, Cl3, very similar. We're just going to replace, if we do the math, we're going to find that we need 4 bonds. We're going to replace 4 of these hydrogens, 3 of these hydrogens with chlorine. And when we do that, we end up with this. And we got to make the chlorines happy. That should be 2 dots, but 2 dots on a line mean the same thing, so we can do it like that. So we look at these bonds. We know the carbon to hydrogen bond is nonpolar, but if we look at our difference in electronegativity between carbon and chlorine, we see carbon's 2.5, chlorine's 3.0, so we end up with 0.5, which is just barely polar. So this is a polar molecule, or polar bonds. To find out if it's a polar molecule, we say, are there polar bonds? Yep. Lone pair of electrons in our central atom. Nope. Is the central atom bound to 2 or more different elements? In this case, they are. So this is going to be an example of a polar molecule. But it doesn't have any carbon to hydrogen, hydrogen to fluorine, hydrogen to oxygen, or hydrogen to fluorine bonds. So let's see, is the molecule polar? Yes. Hydrogen to oxygen, hydrogen to nitrogen, hydrogen to fluorine bonds. There were none. So this is going to just be held together with dipole-dipole forces. And that's just because it's a polar molecule without hydrogen to fluorine, oxygen, or nitrogen bonds. Let's take a look at H2O. If we do the math to do our Lewis structure, we're going to find that we're going to have 2 bonds connecting the oxygen to the hydrogens. To make the oxygen happy, we've got to put the lone pair of electrons on there. Let's see if it's polar. So other polar bonds, let's go look at our electronegativity differences. We've got oxygen and hydrogen. Our difference is about 0.9, so that's definitely a polar bond. So polar bonds, yes. Lone pair of electrons in our central atom. If we go back to what we drew, absolutely. So, lone pair of electrons in our central atom, yes. So that means the molecule is polar. So we come on over to this one. Is it a polar molecule? Yes. And we have hydrogen to oxygen bonds. So that means we're going to be held together with hydrogen bonds. So this is going to be H bonds. And that's because it's polar with hydrogen to oxygen bonds. Stay tuned for the next video. We'll do the last 4 on here. And hopefully we'll get this.